Good morning, everyone. Welcome back. Okay, so we left off with this task, and that was design the C block such that this closed loop system satisfies these three requirements. And if we wanted it to be type 1, then it was already type 1, and so we didn't need to add any integrators. If it was just going to be under control, then we would get the root locus diagram that you see on the right. And the design on the right satisfies the first two conditions. It is a type 1 system, it has a single integrator, it's feedback, and it is stable for all positive gains K. However, it does not really address the third requirement, which is a fast settling time. So then the idea was, if we were able to add a 0, an open loop 0 to the controller, we'd get a diagram that looked something like the left. And the open loop 0, if we're only going to add one of them, has to be real. And so then the process was, it could be in the right half plane, it could be between the plant poles, or it could be to the left of the plant poles. And the design that we settled on was, if you place it to the left of the plant poles, then you'll drag the root locus into this form, and that means that you can place the closed loop poles very far to the left, which improves their settling time. Okay, so that was the idea for advocating for a basically a PD control. So let's actually consider the same problem, but I'm going to change the requirements. Say we need a type 2 system. And so let's consider how that would change the root locus. So again, we've got the plant pole at the origin, we've got the plant pole at -4. And if we need a type 2 system, then we need 2 integrators. So we are going to have to add a second pole at the origin. So this means that our C of S has to be, at the very least, something over S. There could be other stuff, but let's see what happens if this is a simple integrating controller. So let's see if, let's see if anyone can hear me. What part of the real axis is in the root locus for the diagram as it stands?
Everything in the real axis?
Sorry, Tom, I couldn't quite hear you.
Everything is in the real axis?
I disagree. So if I put my pen here, there are 0 things to the right of it, which means this has to be out. So if I put my
I see. So is everything to the left of the -4?
Yeah, there we go. So given this design, all of this is in the real axis. And if we have 3 poles and no zeros, that means 60, a -60, and a 180-degree asymptote. And so because these 2 open loop poles at the origin can't go left and they can't go right, they have to go off into the imaginary part of the plane. And so what they're going to do is they're going to eventually follow those 60-degree asymptotes north and south, and we will get what I believe to be an unstable system for all positive gains K. Okay. Questions on that kind of back of the envelope, quick, dirty analysis?
That was for a controller, right?
So the audio is problematic this morning. I heard most of what you said except for the important part. Brian, can you try again?
Yeah, I can just type it.
So this is not for proportional control, this is for integral control. So this is the diagram for this controller, which has scaling gain k, but integrator here. So I would call this a integral control. No problem. Okay, so I think that we've settled on the fact that this is a poor choice for a controller. So what else could we do? We could, I think it's me. I'm getting a notice that my internet connection is unstable. Okay, so if you miss anything, if it cuts out, maybe type it in the chat. I've got the chat window up and I'll try to repeat myself as necessary. Okay, so integral control is no bueno. Proportional control isn't good either because it doesn't address our type number. So let's modify things. So what do you think? Should we add a pole or should we add a 0? What would help our situation?
Maybe like 2 poles. Yeah, no, sorry, 2 zeros at the origin.
Oh, if we had 2 zeros at the origin, that would kill both of our integrators and it would get us back to type 0.
What about moving your zeros to the left side of the pole?
Sure. So I think what I'm getting is that we should add some zeros. Let's start with 1 0. And the suggestion was maybe try the same trick, right? Because before, put the 0 to the leftmost seemed to work well. Okay, I think that's a reasonable choice. So this is now the 0 at negative z1. And so what happens now? Now we get this region being in the root locus, and we have plus and minus 90-degree asymptotes. Because here, the total number of poles is 3, the total number of zeros is 1. So this gives us 2 asymptotes, which means that they're going to be at plus and minus 90 degrees. So maybe it's interesting to analyze where is the center of mass. Where will this plus and minus 90-degree line lie? So the center of mass is the average of the pole location, so 0 and minus 4, and then the 0 location, so minus z1. Divide that by 2. So what does this look like? This looks like z1 minus 4 over 2. So the bigger z1 is, the more positive this number becomes. So I mean, the way I've drawn it, I think the center of mass is a positive number. You see that? So if z1 were 6, then negative z1 would be to the left of negative 4. And so this would be 6 minus 4, so 2 over 2. So the center of mass would be over here. So there are our asymptotes, and we get this behavior. So maybe you could have foreseen that, but the way to fix that would be to move this 0 over to the right. Then we would move the center of mass to the left. But I hope that you see by doing that, maybe I can do a quick second version. If we do this now, then we get a closed loop hole in there, and we get maybe a center of mass there. This hasn't helped our settling time, has it? It's done everything. It's made it stable. It's made it type 2, but it hasn't really helped our settling time. So I think that a single 0, it's okay, but it's not enough. Questions on why it's not enough?
Is it like not enough because it's only shifting the center of mass by a spot that you don't want it at?
Right. So there are two competing requirements here. Is that dragging the 0 further and further to the left will improve the speed of this closed loop hole, but it will push these closed loop holes to be always unstable. So that means that we lose the first requirement. So if we flip that around and we put the open loop hole here, then we've got a slow closed loop pole, as well as two very slow but stable closed loop underdamped poles here and here. So then we lose out on this one. So you might ask, why not put the 0 over here? That seemed to be our third choice. But I hope you see that if we do that, we get root locus there, root locus there. We still get 90-degree asymptotes, and we'll get breakaways in there. But my attention is here because this means we have a unstable closed loop pole for all gains. So again, we lose out on stability. So I think that a single 0 with an integrator is, you could stabilize the system, but you would not get fast settling time. So I think out of all three options, this was the best because it was stable, but it's not actually any better than our proportional controller was. So let me try one more time. And I think that I heard the suggestion actually at the get-go, which was add a couple of zeros. So let's do that. So if we add a second 0, now actually this raises the interesting point, is that if we have a pair of those, they actually could be complex conjugate pairs. But I think it'll probably make the analysis a little bit simpler if we treat them both as real. But just so you know that now that we have two zeros, they can be complex numbers. We've suddenly opened up that design region for ourselves. Okay, so this design is type 2, right? We've got the extra integrator, so we've got two integrators. That's good. Let's check for stability. So this is still out, this is still out, this is in, this is out, but this is now in, okay? So it looks like, depending on what the integrators at the origin do, we could actually end up with a stable system. So now our overall number of open loop poles is still 3, but our number of open loop zeros is now 2, which means we expect 1 asymptote, which means it's here. This is a good sign. This is a good thing because your asymptote points into the stable part of the plane. Okay, no longer do we have to worry about where the center of mass is. That's a crucial insight here. So here, sigma A does not matter. So if it's positive, we don't care, because think about what we're saying here. The asymptote is pointing due west, and even if the center of mass is way the heck over here, the asymptote is still pointing into the stable part of the plane. So the fact that the center of mass might be quote unquote unstable doesn't actually matter to us at all. Okay, so now what should we do? We know that these closed loop poles that start at the origin can't go left, they can't go right, they have to break away, and then they have to end up here, because one of them is going to head there, and the other one is going to head there, and so we again get this behavior. Sorry, those should meet at the same place. Okay, so I think we have a stable system for all gains, for all positive gains. And we could get a pretty darn good settling time. So again, this is going to be order with 2 zeros. So the more complicated the dynamics get in an open loop, the less and less it looks like a canonical second order system. But we could drag, in principle, we could drag these zeros as far to the left as we want. So let me get another color here. So we could just move these further and further to the left, which would stretch this root locus further and further to the left, which means that we could crank the gain up to maybe put closed loop poles here and here, and maybe a closed loop pole there. So which one of these will dominate depends on the actual like scaling factor of the axis. This one is likely to dominate. And so what we'd like to do is we'd like to move it further and further to the left, which means we have to move this 0 further and further to the left, which we have to move the gain further and further higher. But I think that this is now achievable, that we can get a very fast settling time, provided that we can move the zeros as far to the left as we like. Any questions on that thought process? Okay, so what we've landed on is a pretty handy form for the controller, which is a pole at the origin and 2 zeros and a variable gain. So I'd like you to keep that in your back pocket for just, I don't know, just a minute. And I'd like to make a really cool, I think it's a pretty cool connection. And that is, let's talk about PID controllers, or PID if you're feeling abbreviated. The idea behind a PID controller is that the controller should act on the error, that's the proportional, the integral of the error, that's the I, and the derivative of the error, that's the D. So what you end up seeing is if our error signal is here, which means perhaps this is our reference signal and this is our output signal, plus and minus. So the error signal is going to be copied into 3 branches. In one of these branches, we're going to scale the error signal by some scaling factor. I'm going to call it K prop for proportional. And in the other branch, we're going to integrate the error, and then we're going to scale that by some factor, call it K in for integral gain. And in the other branch, we're going to differentiate, and we're going to scale that, you guessed it, K derivative. And at the end, we're going to add these up. So, and then this is sometimes called the U of S, so the controller effort. So what I'd like you to think of these 3 gains as are weights. You are doing a weighted sum of these 3 branches. So here we've got the error, here we've got the integral of the error, and here we've got the derivative of the error. And I'm scaling these 3 by 3 different weights, possibly 0, possibly some real number, whatever. And then I'm combining them. I'm taking a weighted sum, and I'm saying that is the signal that I send to the actuator. Which then gets fed to the plant, which then becomes the output, which is then fed back. Okay, so I'm skipping all the rest of that to focus on the controller topology. So what I'd like to do now is I'd like to reduce this branch into a single block. I want to call it C of S. Okay, so what do we know here? C of S should be the transfer function that turns the signal E of S into the signal U of S. Now, quick heads up, in this particular, and it's not my notation, but U of S is called the controller effort, and it's just generally used as the signal coming out of the controller. It is not the Laplace transform of a unit step. Okay, so just sorry, we ran out of letters, but the standard notation for the output of a controller is the U signal. Okay, so if I can get U in terms of E, then I think I'll be good. So let's say U of S is K prop times E of S. It's K int times E of S over S. and it's k dir times E of s, times s. Right, so I'm going backwards. I'm taking the Laplace diagram and I'm making basically a differential equation out of it. So I think I can factor the E of s out of everything and write it like this. I can get k prop plus k int over s plus k dir times s. So this is what I'm going to call C of s. This is the controller transfer function. It's not in the form that the final form that I'd like, because it's a sum of things rather than the ratio of two polynomials. So I want to get it as the ratio of two polynomials. How would I do that? Everything has to be over s, I think. So k prop becomes s times k prop. K int is already over s, so we can leave it alone. And k dir is now s squared k dir. Does this look familiar? Maybe we can factor out the k dir, and we get s squared plus s times k prop over k dir plus k int over k dir. So that thing that I told you to keep in your back pocket, go ahead and take it out of your back pocket now. I want you to see that this form that we've got for the controller, the PID controller, is the same as this. Right? The letters are different. The subscripts are different. However, we could always factor this into two zeros. And we'd have a pole at the origin, and we'd have a scaling factor out in front. So I'm reading the chat now. I'm assuming that the PID controller was a better controller to achieve the goals of faster settling time and stable as compared to proportional. Yeah, proportional would not have stabilized the system, nor would it have given us very good settling time. So, yeah, I think the PID, if the goals for this were to get a type 2 and stable and fast settling time, I think PID is actually the simplest possible controller that does that. If you were to cut down any of the degrees of freedom here, I don't think you could achieve all three of these requirements. So I guess what I'm trying to say is that this is a PID controller. So anytime you see a controller with a single integrator and two zeros, what you're looking at is a PID controller, and the derivation for that is here. So just to finish this off, you'll always be able to factor this, roots at negative z1 and negative z2, into something that looks like this. Where, of course, z1 and z2 are functions of the gains of all three, actually, k dir, k int, and k prop. In terms of disturbance rejection, yes, it will help with disturbance rejection as well. The post on Piazza was a derivation that if you include integrators in your C of S, then that will tend to drive the output due to a disturbance input, provided the disturbance comes. So this is answering another chat question. If we had a disturbance coming in here, then the Piazza post that I put up after Monday's class derived the fact that integrators in C of S will help drive the output Y of S due to D of S to 0. And that's different than integrators in the plant. So here it matters what is in this block versus this block. Another chat question. So PID is a proportional controller or integral controller? None of the above. It's both and something else. So the whole idea is that a PID controller is proportional. It's also integral. It's also derivative. That's why it gets all 3 letters. Right? So, I mean, if you like, one way to think about this is that a PID controller could be all P, it could be all D, or it could be all I, provided you set the other ones to 0. Or it could be these 2, or it could be those 2, or it could be those 2, or it could be all 3. I say that because all of these Ks, you can set them to 0. You'd still have a PID controller, but you'd be removing one of your degrees of freedom.
What significance does the a proportional, an integral, and a derivative of the same signal have in terms of?
I'm so glad you asked. Let's try and see what physical meaning we can get from the proportional signal to the error, from the integral of the error, and from the derivative of the error. So this is to say that I hope I'll answer your question with the next slide. Okay.
Cool. Thank you.
Yeah. Let's take the following as given. We have a step input, and we have some underdamped response to that. So input is blue, output is orange. And what I'd like you to do is on this slide, I would like you to visualize what the error signal looks like. So I'm going to do the error in red. But I'm actually going to wait for you to do it first, because I think it's important for you to recall how we define the error signal and what it looks like in the time domain. So I'm going to give you a minute, and I'd like you to take your best guess at what the error signal looks like. So the key is to remember that the error signal is what you want minus what you have. So it's blue minus orange in this case. So in negative time, or I guess before the step fires, the error is 0. And then as soon as blue jumps, the error will also jump. So here R minus Y is 1. And when we get to this point, the error has decreased to 0. Right? Because at this point in time, the reference and the output are the same, so they subtract to get 0. And then the error goes negative. So now we're pretty much going to follow this orange curve, but we're going to mirror it down around 0. And so this, it almost gets to 0. Let's see here. And then in steady state, that's terrible. I thought this would be nicer than doing it on chalkboard. Maybe it's easier to erase. Who knows? So here, this was a valley. This will be a hill. This is a hill, so that means this has to be a valley. And then a little hill, and then a little valley. All right, and then we'll just call it flat from there on out. So this is, I believe, a good representation of the error signal. And this, I mean, in a simple system, acting proportional to the error, so with just proportional control, that can be fine. In particular, if the output is too low, the signal to the actuator is large. If the output is too high, the signal to the actuator is negative. So it tries to bring it back. This is the essence of feedback control. This is your kind of your first this is how we described control back in the cruise control example, right? The speed of the car is too fast, so the engine spins down. The speed of the car is too slow, so the engine spins up. That we described basically a proportional controller. So one way to visualize that is that whenever the error gets small, including negative, then the controller effort gets small, perhaps negative. In this particular system, that scheme is not really doing it for us, is it? Because we're getting this steady state error. So this might be a type 0 system, if you like. So what comes next is, let's look at the integral of the error. So let's do that. How many colors do we have left? Let's do that in light blue. So in light blue, we're going to do integral of the error. And this has a specific meaning. This is not just the integral under the curve, which would just be a fixed number. This is the running integral. So the integral from -infinity to t of the error signal as a function of some dummy variable. Okay, so this is what in 228 I would call a running integral. Well, I'm still calling it a running integral. I'm not sure if your 228 instructor differentiated between a running integral and just a regular old definite integral. So the running integral of the red curve, if we're integrating 0, we get 0. So help me out here. If the error jumps, does the integral of the error jump?
You just get the different slope, doesn't it?
So how much area is there under the red curve just to the right of 1? I think there's just
Oh,
a
I see, so it does jump.
yeah, minuscule amount. So this is one of the properties that we'd like you to get out of 228 is that integrals smooth out discontinuities, right? If I integrate a step, I get a ramp. A step has a discontinuity, whereas a ramp does not have a discontinuity. So this is the same idea. Integrating this error smooths out this discontinuity. So we accumulate positive area until we get to about here. And then we start to lose area. So let me see if I can make this a little bit more clear. So at this point, we are going to start to lose area. So we're increasing until this point, and then the error signal goes negative, which means we lose area until we get to, say, this point, in which the error goes positive, and we gain area under the curve. And then from here on out, we actually keep gaining area. We never lose area ever again. So I think that this reaches its maximum slope here. It might smooth out a little bit until it nearly goes to 0, and then it just keeps rising. Okay, so I think this is my artistic impression of what the integral of the error would look like. And if the error does have a limit as a positive value, this integral is unbounded, right? Because the integral of a constant step, it just runs off as a ramp. So this, you can think of it as a step with some wiggles at the beginning, which means we get a ramp with some wiggles at the beginning. But the idea here is that if your controller were sensing the integral of the error, that signal would eventually get big enough so that you would correct the error. Does that make sense? This is one of the ways people explain why integrators help combat steady state error, is because if the system exhibits steady state error, and that's exactly what we've got here. So this value is your steady state error, and it is non-zero. The integral of that signal runs away. It gets larger and larger and larger. And eventually, that signal in an LTI system will cause the actuator to correct the error. Okay? So let's go to the third leg of the controller here, and let's talk about the derivative. So this is the derivative of the error dE dt. So if the error is flat, the derivative of the error is 0. If the error jumps, does the derivative jump?
If it's a constant, no.
But here, if the red curve goes from 0 to something non-zero, that's an instantaneous change, which you modeled in 228 with a delta function. All right, so this is a jump up. So we end up with a Dirac delta at the origin. But then immediately at t equals 1 plus, right, immediately at the time just after 1, or just after the step fires, we have a negative slope. So it jumps with a instantaneous Dirac delta, and then it starts over here at some negative value until the derivative gets to 0 here. The derivative is also 0 here, and here, and here, and here. So I'm just laying out my zero crossings. So I'm going to get something like, here's positive slope, here's negative slope, here's positive slope again, negative slope, positive, negative, and then eventually the error curve flattens out. And so we get 0 derivative in steady state. Okay, so in the time domain at least, we have the pictures of the 3 signals that our PID controller could act on. And again, if the controller acted on these signals, then the response would be modified. So we are taking a snapshot of an uncontrolled system and kind of overlaying what would happen if we introduced control to it, but we're not then using that to refix the output of the system. So this is just a kind of a fixed snapshot about what these 3 components will look like. And the reason I bring this up is, well, a couple reasons. First is to show you that if the steady state error is non-zero, then the integral of the error runs away. So that's one reason why integrators help combat steady state error. The other thing that I'd like you to see is that whenever the integral signal goes low or valleys, the derivative signal goes high or crests. So I'm looking here and here. And I'm looking here and here. And that's because at the heart of it, this error signal is sinusoidal. It's got some damping factor out here. But if you were to integrate this, you would get a cosine. If you were to differentiate this, you would get a negative cosine. Or the other way around. I think it's the other way around. Yeah. The point is, these two tend to have opposite signs. So when the integral signal goes low, the derivative signal tends to be high, and vice versa. This is another key aspect that introducing both integral and derivative control in parallel will help the derivative will help combat the bad stuff of the integral, and the integral will help combat the bad stuff of the derivative, right? Sorry, but there's no free lunch here. We're going to see the trade-offs that are involved here. And my argument is that because the derivative and the integral are parallel to each other, they're not cascaded. That's key. I'm not taking the integral and then the derivative, which would do nothing for me, right? It would just undo everything I've done. I'm doing them in parallel and adding their weighted combination here. Their weighted combination the integral will be high whenever the derivative is low, and the derivative will be high whenever the integral is low. So they will tend to, at least in the transient regime, cancel each other out. Now that statement does not hold in steady state. Clearly, the derivative goes to 0, the integral of the signal goes to infinity. So what I said only really holds in the transient regime. Let's see, where are we here? Another way to think about this is that the error signal gives you kind of the present. I don't want to. State it's got a special meaning in controls, but the error signal, if you're just looking at the error as a function of t, it gives you the present error, like the present state of the system. If you look at the integral of the error, this tells you all past states, or it gives you a sense of history. That is, if the integral of the error signal is large, then the system has had error for a long time, and that means that something needs to be done about that, even if the current error is not particularly large. Okay, do you see how those two concepts are different? I can have a very small e of t, but I can end up having a very large integral of e, and I would like the large integral to make me do something. That would mean that I'm acting on the history of the system, not the present state of the system. And so the third fork of this trident is the derivative. And I want you to think about the derivative of the error as an anticipation of where the error will go. And I hesitate to use this word, but there is some power in thinking about this, that the derivative tells you the very near future. Not the entirety of the future, but if I know the slope of a curve, I have a pretty good idea where that curve is going to go in the next time instant, right? By a linear approximation, if you like. And so this is a powerful way to think about the PID and all three of the branches. Is the error signal or the proportional signal tells you about the present error, the integral signal tells you about the past error, and the derivative signal tells you something about the future error. And all three of these are valuable information. All three of these should tell you if your controller, if your actuator should make an effort. Is the integral recursive? I don't know if I understand. So there's a question in chat about, is the integral recursive? The integral can go to 0. If the error goes positive, goes negative, and then settles out at 0, then the integral of the error can go away. Like that's actually what we'd like to have happen. And I mean, if you want to view this as a discrete time system, then yeah, the integral is yesterday's integral plus today's value times the time change. So you could think of it as a recursive system like that. But that's again, that's kind of a 328 view of this. It's not wrong, but it's also not exactly part of this class. Did that answer your question, the person in chat? Okay, cool. So before we go on, because I'm going to do another demo with PID, I'm going to do it in Simulink to show you how all of these come into play. I want to highlight one more part of this graph. So it's going to get a little bit messy. So I want to take a pause here and ask if there are any questions before I make it even messier.
You said that eventually we hope that the integral of the error signal would go off to 0. How could you just repeat what you said when you said that?
So I think it's helpful to look at the block diagram. Eventually, if the system does what we want it to do, then eventually the error is 0. Do you agree with that?
Mm-hmm.
If the error is 0, then I'd really like for this LTI system, this subsystem, that the effort is 0.
Yeah.
So the problem is that this branch stores the past history of the error. And so if the current error is 0, this branch will be 0. If the derivative of that is 0, then we get 0 here. So we need this to be 0 as well in order for there to be a 0 signal out here.
Mm.
So yeah, what we'd like is for the error to go positive and then go negative, and then eventually this part of this, this branch, I'd like that to go to 0. I'd like this to go to 0. I'd like that to go to 0. I'd like the sum of them to go to 0. If it doesn't, that means that we haven't reached steady state. I think that that's the simple way to put it.
I see. Okay.
Yeah.
Thank you.
So Newman asks, is it mainly true for transient or steady state too? Yeah, what I said is true regardless of transient or steady state. In steady state, we hope the derivative goes away, and so we hope the derivative actually doesn't tell us much. Or I guess the derivative tells us that we're not changing. Yeah, so it still tells us that it's just not nearly as useful.
Where is the plant in the PID?
It's we haven't described it. It's down here somewhere.
Okay.
Okay.
Sorry.
Yeah, go ahead.
I have another question. So in this picture, it looks like the derivative part of the controller seems to have a large effect on the initial transient response, because it jumps up super big, so that'll like correspond to a big response in the controller output, while the integral is more about steady state value, where it'll respond like in the long term. Is that kind of another understanding of what this PID does?
That's absolutely right. When we get to the topic of tuning PID controllers, the whole idea is that you only add as much integral control as you need to fix the steady state error. And then you bring in the derivative control to combat the overshoot that you get from introducing the integral control. And the key part of this is that the derivative control doesn't undo the good stuff that the integral control gives you, because the derivative is going to go to 0 in steady state, whereas the integrator is going to keep fighting to 0 out the system. So yeah, that is an insightful and a correct way of interpreting what's going on. Okay, so the last part of this diagram that I want to call your attention to is actually this point right here. If we were doing, say, proportional and integral control, then it's important to see that at this point, we're happy, right? At this point, the error at, this would be t rise, is 0. And that makes us as control engineers happy when the error is 0. However, look at what is happening at the integral signal at that point. And again, what we're looking at is this area. The area between when the step fires and when the error first goes to 0 is known as the integrator windup. Integrator windup. And what it means is, at this point in time, the proportional controller is happy. The proportional controller says, everything's good, the actuator can calm down, right? Because this signal is 0. But the integral is going crazy, because the integral is saying, look at all this past error. We need to keep acting. We need the actuator to keep going. And so this phenomenon of integrator windup means that PI controllers will always overshoot. And the explanation for that, again, is at this point in time, the P is 0, but the integrator is positive. And so the actuator is going to keep driving the system beyond this happy equilibrium point. Okay? And so this is the first introduction to why we need derivative to combat this. More on that on Friday. I'm out of time. Thank you very much, everyone. And
is there always overshoot with the PID controller or just the PI?
No, so this is true only for PI, because if we introduce the derivative, then we get this negative effect, and so we can actually overcome that. So
okay.
This statement is exactly what I meant to say. PI control will always overshoot. That's why you usually see PID and not just PI. Okay? Cool. I will see you Friday or in office hours. Thanks, everyone.